Good day, everyone. Welcome to Nanoengineering Cellulose for Environmental and Biomedical Applications. I'm your host, Mike Lasecki, and this webinar is hosted by ATE Central. ATE Central is the information hub for the ATE grantee community. You can find out more about them and the webinars at atecentral.net. This webinar is brought to you by a collaboration between NCI Southwest at Arizona State University and the NAC network at Penn State University, with support from the National Science Foundation. This is a good time to remind us that the opinions offered in today's webinar do not necessarily reflect those of the National Science Foundation. That's me on the left, Mike Lasecki. I work at Luca Partners. You've heard communications from Janet Pinhorn. She's part of our team. We also have Shannon as an IT support person helping us with this webinar. Thank you very much. Joining us in the background today is Bob Ehrman. He's the managing director of the NAC network at Penn State. Bob, I know you'll be putting some things into the chat window and you'll meet people from there. Now let me ask Trevor Thornton, who is professor at Arizona State University and head of the Nanotechnology Coordinated Infrastructure Southwest at that university. Trevor, would you come along? Come on, just say hello for a minute. We'll do a last minute audio check.
Very good. Thanks, Mike. Hopefully the internet will be able to keep up with us today. I'm very excited to learn about nanocellulose today and Dr. Shaky's talk. So very good. I'm sure there'll be opportunities for questions and people can post questions on the chat and we can address those as necessary. Well, very good, Bob. I'll hand over to you. My Adobe presenter is taking a little bit of time to load here, but hopefully that will catch up and we can proceed with the webinar.
I'll just say very quickly, welcome to this webinar, and it's a pleasure to be a part of this. And again, I won't be saying much. Trevor will be the main person that will be, and Mike will be the main people that will be presenting here. But we really welcome you to this webinar and appreciate your attendance, and hopefully it'll be very worthwhile. And I've seen Dr. Shaky's talk before, and I think you're going to be very intrigued about some of the really great stuff that he's doing. Mike, I'll turn it back to you.
Well, I'm guessing Mike might have lost his internet feed since he's gone quiet, and maybe this, and I must say I'm also having trouble. The Adobe presenter wheel keeps spinning. Bob, if you're online, are you able to see Dr. Shaky's slides?
I can see his slides. Can you hear me, Trevor?
Yes, I can hear you just fine. I can't see his slides at the moment. Yes, Bob, I can hear you fine.
Okay. So Shannon, maybe you can help to. Why don't we turn it over to the next slide, Shannon, and we'll move from there. So I'll introduce Dr. Shaky. I met Dr. Shaky actually several months ago, earlier this year, at our Millennium Science Cafe, and he did a 10-minute talk, and I was enthralled with the work that he was doing, and I asked him to be this is here at Penn State, and I asked him to be a part of this webinar, and he readily accepted. He's actually helped us out in another professional development area too, so he's an assistant professor in the chemical engineering department. He's been here since last year, but I'll let him talk. I'll let him introduce himself, and we'll move on to the introduction. So, Dr. Shaky, if you would want to take over the microphone and the slides, I'll turn it over to you.
Mike, thank you very much, Bob. Trevor, thank you all for having me here today. It's indeed a pleasure to spend an hour with everyone here. I'm truly thrilled by the number of attendees, and I'm sure it's gonna be a fun event. So thank you everyone for being here. I will talk about nanoengineering cellulose for environmental and biomedical applications today. As introduced by Bob, I am Amir Sheikhi. I'm an assistant professor of chemical engineering and also biomedical engineering by courtesy here at the Pennsylvania State University and State College. A little bit about myself in this slide. This is me, of course. I did my undergrad in chemical engineering and my master's also in chemical engineering back in my home country, Iran, at the University of Tehran. And I continued my education in chemical engineering. I moved to Montreal, Canada. At McGill University, I completed my PhD, and I moved to another basically College of Science. I did a postdoc in chemistry at McGill University for 2 years, and I drove down to Boston to Harvard MIT Health Sciences and Technology to do a postdoc in engineering and medicine, and my lab moved to UCLA. So I moved to UCLA with my lab to complete my project. So by this time, you would have thought about the travels of Marco Polo, and that is really me in the past couple of years, traveling from Middle East to Canada, and then US East Coast and West Coast, and then back to East Coast, Central Pennsylvania last August, and starting as an assistant professor. Fun fact about me is that I was born in Tehran, the capital city of Iran. This is the picture of Tehran in a very beautiful and unpolluted day, I should say. When I was a kid, I wanted to become an astronaut. I was so obsessed with astronomy that I kept collecting astronomy journals to the extent that my parents got worried about me because I stopped playing with my friends outside. At that time, I learned that the force exerted on the human body during the launch of the rocket is can be more than 4 times the body weight. So the ill-fitting dental fillings could become loose or fall out. So I took a very good care of my teeth. I was obsessed with my teeth. Probably after astronomy journals, my teeth were my second obsession at that time, and I didn't have any major problem with my teeth ever since. Well, as you can see, I never became an astronaut, and instead, a couple of years later, I became a chemical engineering faculty. My hobbies, I really love swimming. It's been a while that I haven't done that, and I hope that I get back to that routine. My favorite food is barberry rice with saffron chicken, and this is a Persian food, so if you can go to a Persian restaurant and try it, I should say definitely do it. It is truly delicious. Some keywords about my research are experimental soft materials, biomaterials, living materials, environment, tissue engineering and regeneration, and bioseparation. Here's the front page of my lab website. I finished compiling my lab website a couple of days ago, and I shared the link on LinkedIn. So please feel free to visit us at www.shakylab.com. To learn more about our research, our publications, team, teaching and outreach, and also our facilities and possible collaboration opportunities. This image is for a couple of months ago, so we are almost doubled in size now. Let me start today's presentation with one question. How can bio-based soft materials and biomaterials impact society? Well, the current society is suffering from soaring population growth and imbalanced supplies and demands, shortage of ready-to-use remedies, and urbanization, all of which imposing serious concerns and challenges to water, healthcare, food, and energy sectors. And I believe that by engineering new materials, we can address some of these challenges. And there are 2 questions that we keep asking ourselves in our lab to address these challenges. Number 1, how can natural bioproducts be micro and nano engineered to overcome the persistent bottlenecks of current synthetic materials? And the second question is, how can the sophisticated structure property relationships in nature be mimicked in the lab to address everyday life challenges? Our contribution to this is through four main material platforms: microfluidic enabled biomaterials, biocolloids and biopolymers, which is actually the focus of today's seminar, biomimetic materials, and colloidal gels. And today we will talk a little bit about the biocolloids and biopolymers that we are interested in and we use for water and healthcare applications. Let me tell you a little bit about shocking statistics driving us in our research. Every 20 seconds, a child dies from not having access to clean water. In fact, 2.5% of the water in the world is fresh water, from which 70% is frozen, 30% is underground, and less than 1% is accessible to us. And we have been continuously contaminating it. More than 38% of men and women will be diagnosed with cancer at some stage of their lifetime. More than 85% of them will suffer from one or more side effects of chemotherapy. 1 in 50 people will be diagnosed with brain aneurysm, which is the bulging of blood vessels in the brain that may rupture and kill that person. 40% of pregnancies globally and 50% in the US are unwanted, and we are currently experiencing organ shortage in the world. And what we do in our lab is to try to use the most abundant materials in the world to address some of these challenges. We use the most abundant biopolymer in the world, which is cellulose, and we engineer it to make a newly emerged type of nanocelluloses called hairy nanocelluloses for the applications that I'm going to talk about today. We are also interested in silicon and layered minerals based on silicon to make injectable shear thinning materials for minimally invasive medical procedures. And we are, of course, highly interested in the most abundant protein in the body, which is collagen, and using the denatured version of that, which is gelatin, and convert it to modular materials using our microfluidic devices to provide solutions for accelerated tissue engineering and regeneration. And all of these materials are part of an amazing class of materials called soft materials, and all we do is to micro and nano engineer them. What are we going to talk about today? The focus of today's talk is nanocelluloses, and particularly a newly emerged type of nanocelluloses called hairy nanocelluloses, and I will talk about some of the applications of this class of nanomaterials, including scale inhibition, biomimetic mineralization, scale-resistant interfaces, water remediation, and some other applications such as nanocomposites, bactericides, humidity switches, and rheology modifiers. What are nanocelluloses? Let's take a look at the plant cell wall and find one of the components of that, which is cellulose fibers. Cellulose fibers are made of bundled microfibrillated celluloses, which are made of microfibrils. These microfibrils are made of alternating crystalline and amorphous regions. Well, this is one of the models of cellulose fibers. The exact location of this crystalline and amorphous region is still a mystery, and there is a lot of research going on to understand that. Depending on the treatment on this cellulose fiber, if we get rid of all the amorphous regions, for example, by a strong acid hydrolysis, we end up with these crystalline nanoparticles which look like needles. We can also treat cellulose fibers using a mechanical shear and disintegrate it into long fibers that we call microfibrillated or nanofibrillated cellulose, couple of micrometer or hundreds of micrometer long, couple of nanometers thick. So these micro or nanofibrillated cellulose really resemble spaghetti that we eat every day. This aggregated and bundled structure of these fibers, and cellulose nanocrystals remind us of rice grains, these nano needle shape particles, a couple of 100 nanometer long and a few nanometer thick. And of course, I don't need to mention that all these materials are made of cellulose with these glucose-like units with reducing ends and non-reducing ends. The benefit of these materials is that they are biorenewable, they're biodegradable, they're cost-effective, environmentally friendly, and they have a very large surface area, enabling us to use them for a range of applications. And let me show you what happens if you increase the concentration of these materials. You form a physical gel, as I show here. Let me tell you a little bit about the history of this. About 2 centuries ago, the discovery or the realization of cellulose was done by Anselm Payen, a French chemist who realized the cellulose chemistry, and it took the field a little bit less than a century to understand what nanocellulose is and to observe nanocellulose. So Bengt Ranby observed that almost every time that you treat cellulose fibers with a strong acid, you end up with these tiny particles. At that time, they called it cellulose micelles. And ever since, nanocelluloses have found applications in a broad range of disciplines. They have been used in nanocomposites, films, hydrogels. They've been used as rheology modifiers, coatings, aerogels, fillers, optical materials, and self-assembled materials, and so forth. Here is a summary of the applications of conventional nanocelluloses in food, water, and energy sectors in different forms, as I mentioned: hydrogels, liquid crystals, emulsions, aerogels, polymers, foams, and so forth. The number of publications in this field is just amazing recently. So it started picking up around 2003 or 2004, and over time you can see this exponential growth, and only in 2019 we have more than 1,800 papers on nanocelluloses. So as you can see, it took the field, after the discovery of nanocelluloses, about 50 years to start realizing the true potential of these materials. Who is using nanocelluloses? Mainly material scientists, chemists, and chemical engineers actually use this material, and the application of this material goes beyond this. In a lot of engineering disciplines, in biochemistry, agriculture, environmental science, energy, medicine, and so forth, we can find numerous examples of the applications of this material. Six universities in US came together: North Carolina State University, Penn State University, Georgia Tech, Purdue, University of Tennessee, and Oregon State University to form Cellulose Nanotechnology Research Consortium because of the importance of these materials. And of course, USDA Forest Products Lab partnered with University of Maine to produce these conventional nanocelluloses at industrial scales. But today's talk is really about a new type of nanocelluloses that we call hairy nanocelluloses, which can address some of the fundamental limitations of conventional nanocelluloses in terms of charge density, colloidal stability, and the production method. The first challenge that we are going to talk about is scale inhibition. But before that, I may pause here. If anyone has any questions, I'm more than happy to answer.
Dr. Shaky, this is Trevor Thornton. Yes, did I hear you say that we don't really have a good understanding of what these molecules look like? The reason I ask
is the plant cell wall is a mystery. Please go ahead.
Yeah, so I was wondering if people have tried using electron microscopy, transmission electron microscopy, even cryogenic TEM. I wonder whether those applications might help.
Yeah, people have been using all these methods, even more sophisticated imaging methods. It's really the difficulty here is to image the amorphous regions of cellulose. So under TM, it is very difficult or almost impossible to see these regions and how the plant cell wall is formed and how these fibers and the components of these fibers are formed. This is still a mystery and the subject of actually millions of dollars of basically worth research in US and in the world. So there are some models on that, but there is no certain model that has enough experimental basically proof. Any other questions? So I see some questions in the chat, but I'm not sure if I have to answer them now or Mike, you would like me to wait for them.
Amir, let's wait and go ahead and we'll have another question break. Thank you.
Sure, sounds good. Okay, let's continue with the first challenge that we are going to discuss. Scale formation. What is a scale? What is the scale and a scaling? Scaling is the formation of sparingly soluble salts, such as the salts of carbonate and sulfate with calcium, magnesium, barium, which tend to adhere to unit operations such as cooling towers, evaporators, digesters, pipes, heat exchangers, and so forth, as you can see here, which increase the resistance against the heat, mass, and momentum transfers. They impose serious challenges to water-based industries. These are operational and economical challenges. The way that the industries have been treating scale can be categorized into three main basically methods. Acid treatment. Some industries used strong acids to dissolve some kinds of scales. Despite the fact that some of the scales can be dissolved in strong acids, we should notice that at low pH conditions, the corrosion will be a serious phenomenon. So it's not a favorable event. Ion exchange membranes have been used for this purpose to simply remove all the ions that precipitate, but they are highly expensive. And micromolecular additives have been the gold standard in the field to add to water and prevent the formation of this scale as compared to waiting and then removing these scales after their formation. So these macromolecular materials have some drawbacks despite their pretty good performance. They are typically non-biodegradable. Their backbone is sometimes toxic, and they are made of phosphorus and nitrogen based functional groups that are excellent nutrients. And when they are dumped in free water, they result in the so-called eutrophication process, which is the excessive growth of sea plants resulting in the elimination of fish due to preventing the fusion of oxygen and sunlight into the water. You have seen this green water. So that is an environmental problem. The presence of only 0.1 ppm of phosphorus in water will label it hypereutrophic. And there are currently some regulations even against using phosphonated detergents, including the limitations in Pennsylvania. How do we simulate the scale formation in the lab? That is definitely a process that may take a couple of months or even years in industry, but the way we do it is through using an electrochemical method called chronoamperometry, in which we fix the voltage exerted on a rotating disc electrode in a saturated solution of calcium and bicarbonate and measure the current versus time. That's why it is called chronoamperometry, measuring current versus time. So if the electrode doesn't scale, the current will look like this. There is no significant change in the current, but as the scale is formed, as you can see here, the current decreases until it reaches zero because the scale is an insulating material. Okay, so Now, by applying this voltage to the electrode, what happens is that we form OH minus on the electrode, which shifts the equilibrium of carbonic acid towards the formation of carbonate, which reacts with calcium to form calcium carbonate, and the scaling forms and the current goes down to 0. So in the future slides, whenever you see this figures, if the current is almost constant, it doesn't drop, it's a good sign that the system doesn't scale, and if it drops, the system starts scaling. So the additives that are used for this purpose, particularly the phosphonated ones, are excellent materials to prevent the scale formation, because they are typically highly phosphonated and they have flexible backbone. So I was thinking about using conventional nanocelluloses, something that no one has used for scale inhibition. Cellulose nanocrystals, as I mentioned, or oxidized version of that. This is a tempo oxidized cellulose nanocrystal with a larger amount of carboxylic acid, and also nanofibrillated cellulose or cellulose nanofibrils with even higher charge content. So I added them to the scaling water, and as you can see, there is almost no difference between the scaling performance of the water when there is nothing in the water and when we add a large amount of these nanocelluloses. Don't forget that our competitor is the phosphonated industrial anti-scalant, which is effective in our condition at less than 10 ppm concentration. And here you can see that 6 times that concentration doesn't have that much effect. Then I thought maybe the problem is the charge content. So what we did was to use carboxymethyl cellulose with a more charge on that, but the scaling result is still not good. And the reason for this is because these conventional nanocelluloses don't have enough charge on their surface, and this fully solubilized cellulose chain does not have enough structural flexibility. So we thought, can we be this blue fish and swim against the flow and engineer cellulose in a way that it performs as an anti-scalant? And we took a look at plant cell wall, and as I mentioned, it is made of crystalline regions, as you can see here, and amorphous regions. So what we did was to preferentially oxidize the amorphous regions using some chemicals that I will introduce you in the next slides, and increase the solubility of the fiber from the amorphous region to break it down into cellulose nanocrystals that are sandwiched between 2 layers of highly functional amorphous chains. That's why we call them hairy nanocelluloses. Here is how we do it. So we start with cellulose fibers. It can be a piece of paper or pulp. We do iodate or periodate oxidation to convert the glucose ring, open the carbon 2 and 3 and convert it to aldehyde groups. And what we have is an intact fibrous structure. And depending on further modification, whether with chloride to oxidize these aldehyde groups into carboxylic acid, or by heating the fibers at 80 degrees centigrade, or reacting it with an amine functionalized material through a Schiff-based reaction, we can make a family of negatively charged, neutrally charged, or positively charged nanoparticles. So these materials are now looking like water. So there is nothing to see by naked eye as compared to these fibrous slurry, because the size of these fibers have reduced to nanoscale now. Here is the conductometric titration of these nanocelluloses, particularly this electrosterically stabilized nanocrystalline cellulose. And we can see that the charge content is about 6 millimole per gram for this particular product, which is more than 1 order of magnitude higher than conventional nanocelluloses. And if we take a look at these particles under AFM, we can see that they are very similar to conventional nanocelluloses with respect to their crystalline body, as you can see here. So this is me doing this reaction at McGill University when I was working in Theo van de Ven's lab, tearing papers and then putting them in water, soaking them, removing the water, and then reacting the pulp with periodate. As you can see here, we also need to cover it from light because it will get deactivated by light, and then stopping the reaction by adding ethylene glycol, and then we end up with this intermediate material, which is dialdehyde modified cellulose. Then we can further oxidize it with chloride and hydrogen peroxide, and what we end up with is this clear solution of hairy nanoparticles. Of course, the side product of this is a fully solubilized polymer that we separate through co-solvent addition, and I don't go through the details of that here. So here is the TEM image, transmission electron microscopy image of conventional nanocelluloses and hairy nanocelluloses. As I mentioned, it is very difficult to see the amorphous region under TEM, so their crystalline body looks very similar. But there are some striking differences in terms of functional density, as I mentioned, and also colloidal stability. When we increase the salt concentration in a suspension, basically dispersion of conventional nanocrystalline cellulose, what happens is that their size increases because we screen the diffuse double layer around them. They can explore closer vicinities to each other, and they aggregate and they form this gel-like material. So you can see here that the size increases. This is the hydrodynamic size measured by dynamic light scattering. What happens to this hairy nanoparticles? As we increase the salt concentration, these hairs shrink, and not only they don't aggregate, as you can see here, they remain in their dispersion form, their size keeps decreasing because, again, these hairs shrink and their size decrease. We can also functionalize these hairs with chemical groups that specifically react with each other. So we can have a batch of this hairy nanoparticles and functionalize it with azide, and have another batch and functionalize it with alkyne, and conduct alkyne azide, the copper catalyzed cycloaddition. And what we end up with is to see that these materials, these nanoparticles, attach to each other from their ends to make this long micron scale fibers. Of course, there are some basically heterogeneities there, but this is one of the indirect proofs that these hairs mainly exist on the poles of these particles. Another great work to show this is by Theo's group, which showed that when we functionalize hairy nanoparticles with a dendrimer, PAMAM, which is amine functionalized, and then tag it with negatively charged latex particle, we go from this state, which is individual particles, to the aggregated particles from their end. So you can see here that these nanoparticles mainly attach to each other through their end. So this is a very interesting work that recently got published. Another indirect proof of the existence of these hairs on the end of these particles, which can be an indirect proof that the cellulose fibers are made of alternating crystalline and amorphous regions. As I mentioned, this is still a mystery. So now these hairy nanoparticles can be made in different forms. We can have particles with long hairs, as you can see here. The longer the hair, the more charge we have on the particles. Of course, there is a limitation, the upper limitation for this charge before the whole particle falls apart and solubilizes. And we can take these particles to the barber shop and start cutting their hairs by simply treating them with strong acid. And what we did was to make this family of hairy nanoparticles, and we tested their performance as an anti-scalant, as I mentioned. So here is the chronoamperometry figures, and I hope that you remember what we said about them. When the current is almost constant, it shows that the system doesn't scale. And as you can see here, about 16.6 ppm of the nanocellulose with the longest hair can act as an anti-scalant. And this is a threshold anti-scalant, meaning that we need ppm levels more than 3 times, more than 3 orders of magnitude to lower concentrations than the concentrations of precipitating ions in the solution to prevent the scale formation. And as we cut or trim these hairs, we can see that the anti-scaling performance of this nanoparticle decreases, which shows that conventional nanocelluloses can never perform as anti-scalant because their charge content is well below 2 millimole per gram. For, let's say, conventional nanocelluloses, the charge content is well below 0.8 millimole per gram. So the reason that these hairy nanoparticles can perform as anti-scalant is that they have enough functional group density on them, and also we have opened the glucose ring from carbon 2 and 3, so now the structure is flexible. So we are benefiting from both structural flexibility and high functional group density. Here are some more results on the performance of these nanoparticles at different temperatures that I'm not going to go through the details. The lower the temperature, the less material we need to prevent scale formation, and that is not because the performance of these nanoparticles improve at lower temperature. It's simply because the impaired scaling kinetics at lower temperatures. We can also take it one step further and fully solubilize these nanoparticles into dicarboxylated cellulose, and the performance can further be improved in a way that we can now prevent the scale formation with concentrations of less than 10 ppm, which is interesting because that can compete with current phosphonated non-environmentally friendly scale inhibitors. And of course, when a system is partially scaled, as you can see here, we let the system scale and then we add these nanoparticles at a certain time point, we can still prevent the formation or prevent the further scaling of calcium carbonate. So this solution can also be applied to systems that already scaled. Here is an image showing how a water tank is blocked due to the formation of these scales, and when we have these cellulose-based nanoparticles, there is no scaling, and then we can have the flow of water. And this was the cover image of Materials Horizon in 2018. This work got highlighted by many news outlets, including Uric Alert and Water Technology and so forth, as the first cellulose-based scale inhibition technology. So in the next part, I will talk about the mechanism and how this scale inhibition takes place and how we can use that for biomimetic mineralization. But I think it's a good time to pause and see if anyone has a question.
Amir, it's Mike. There is a question. It has to do with the economics of the system. And so are these economically feasible materials, or how does it work compared to conventional antiscalants?
That's a great question. So hairy nanocelluloses, particularly we're talking about anionic hairy nanocelluloses, can be produced with a couple of dollars per kilogram only if we can recover the reactants, not completely, but with a yield of more than 97 or 98%. So we haven't started working on the scale up of this material, but if we come up with a process that is economically feasible, and theoretically it is possible to do that, because one of the main components that needs to be recovered is periodate, and there are standard methods for doing that, then I can say that most probably they can compete with industrial anti-scalants.
Okay, good. Trevor, let me turn to you. Is there a question from yourself or from the audience?
So I have a question that can wait till the end if there's someone in the audience who wants to ask. So I'm seeing that, yeah, somebody is
Go ahead with
asking.
your question. Yeah, go ahead.
Yeah, well, I'm seeing that someone's asking, is this cellulose used in preparation of craft paper? I'm not sure what that means. Dr. Shaky, do you have a comment about that?
Yeah, this is the yeah, so sure. Our initial material, our starting point is kraft pulp. So, so this is a delignified and bleached cellulose. Yeah.
So I imagine that's pretty low cost, right? We all know paper's cheap.
Yeah, the initial material is really not the limiting factor. The recovery of the reactants is a key factor in producing this material at a very cost-effective manner.
Very good, thank you. Why don't you continue
Amir,
this
it's Mike.
biomimetic
Well,
mineralization?
I'm gonna jump in with one more if I could, Trevor. Do these materials degrade with use over time, or can they be recycled after they've been degraded? That was one of our questions.
So this is cellulose, similar to the leaves that
Sure.
fall down from trees and they degrade. Over time, they may degrade depending on the condition. For example, in extreme acidic conditions, of course, they undergo hydrolysis and they degrade into their unit. Again, depending on the process, we may or may not need to or want to recover them
Sure.
because they are relatively cheap, and we may not even need to do that. So we can just add it to water and let it go.
Good. Let's move forward. We're interested in hearing about what these snails are doing here on this slide. So go ahead.
Awesome. So biomimetic mineralization is done in a lot of animals, particularly sea animals. As you can see here, these beautiful structures are a result of a process in which the crystallization of an inorganic material is affected by an organic material, such as a protein. There's no way of getting such beautiful structures in the lab without having that kind of templating or basically additive effect. Let me tell you what happens when we mix calcium and carbonate in the lab. What we end up with is these rhombohedral structures of calcite, the most thermodynamically stable polymorph of calcium carbonate. Even when we add conventional nanocelluloses to a precipitating solution of calcium and carbonate, we still get these rhombohedral structures, the calcite, the most stable polymorph of calcium carbonate. So these particles cannot change the polymorph of calcium carbonate. But let me show what happens when we add hairy nanoparticles, particularly the anionic one, to the solution of calcium and carbonate. What we end up with is still calcium carbonate, not surprisingly, but in a flake-like structures, as you can see here. This flake-like structure, we can zoom in here, and this is really the structure, the beautiful structure that you can see here, which is the least thermodynamically stable polymorph of calcium carbonate, vaterite, that I will explain in the next slide. But here, what I want to show you is that these structures are very similar to the calcium carbonate structures that form in the ear bone of salmon. And if the structure is not like this, if it doesn't look like this, the salmon will have problems finding its direction under the water and keeping its balance. So having this flake-like structure plays a vital role in the life of salmon. These are some other images of the flake-like structure of calcium carbonate that I got in the lab. So you can see this large micron scale flakes that can be basically decorated with these lenticular particles through a secondary crystallization. And you can see these small bumps on these crystals as I'm showing here. And we can further study these structures by basically picking a couple of them, as you can see here. This is an SEM image, coating them with a conductive metal, cutting this crystal using FIB, a focused ion beam. As you can see here, we're cutting it from two ends, picking it up and transferring it to a TEM, transmission electron microscopy grid, and examining it under TEM, as you can see here. So these two are really these two bumps here, or better to say here, because we cut part of it. And as we focus on these structures, we can see that these bumps are made of alternating amorphous calcium carbonate, the least thermodynamically stable polymorph of calcium carbonate, and vaterite, the least thermodynamically stable crystalline polymorph of calcium carbonate. So these two polymorphs cannot be obtained at lab condition by simply mixing calcium and carbonate. And the way that ENCC is changing the polymorph is similar to the way that proteins inside the body are changing the polymorphs of calcium carbonate. So these can be used for biomimetic crystallization, which plays a significant role, for example, for hard organ and tissue engineering. And I don't really go through the details of this.
Amir, it's Mike.
And before we talk
One of the
about
questions that has
scale-resistant
come up is,
interfaces,
you mentioned
I will pause
cellulose
for
degrades, and we
possible
understand
questions
that,
on
but what
biomimetic
about these
mineralization and the mechanism of
nanocelluloses
scale
in vivo
inhibition.
conditions when they're either adsorbed or ingested by living things? Is there any issues? You know, people worry about these various nanotechnologies and their influence in the environment. Has there been any studies like that? Am I asking the right question?
Yeah, no, this is an excellent question. There have been studies about the in vivo performance and fate of nanocelluloses in different organs. So what I would say here is that cellulose itself as a scaffold for tissue engineering and regeneration is probably not the best material, because humans don't have the enzyme to degrade it. So we don't have cellulase to degrade it. Of course, like animals like cow and other animals can eat it and digest it, but for us it is more like a 0-calorie food additive that can basically go through the GI tract and act as a fiber. And for implanting this into the body for tissue engineering and regeneration, unless we come up with a way that it biodegrades over
thanks
time,
for that
it
answer.
wouldn't
You know,
be
in the interest of
a
time,
perfect
there's
solution.
about
That's why,
12
for
minutes or
example,
so
in
left.
my
Why don't you
lab,
go
we
ahead into the
use other types
presentation,
of
and we'll save our
biopolymers,
questions
such
for
as
the end.
gelatin, which mimic the extracellular
Thank you.
matrix for tissue engineering applications. Sure. So we talked about adding nanocelluloses, and particularly hairy nanocelluloses, to inhibit scaling. Can we eliminate the necessity of adding these particles to water to prevent the scale formation? Can we make interfaces that are anti-scaling? Well, we have shown that incorporating these hairy nanoparticles into conventional water treatment membrane materials, such as cellulose acetate, will increase the scaling time by up to a factor of 3. And the reason that we think that this happens is by providing an ion-rich environment at the interface which eventually will prevent the diffusion of precipitating ions towards the interface. We can also go ahead and coat surfaces with these hairy nanoparticles and obtain scale-resistant interfaces. And here you can see our quartz crystal microbalance experiments in which an uncoated surface scales and this resonance frequency increases, which shows the deposition of mass on the balance, and the surfaces that are covered with hairy nano celluloses do not significantly scale. Again, to the favor of time, I'm not going to go through the details. In the next slides, I will just go through some of the applications of this material, but I'm more than happy to answer questions. For water treatment, as we mentioned, these hairy nanoparticles can be highly charged. One of the concerns in water-based technologies is the release of heavy metal ions. They are not as cool as you see in this picture. Many of them result in serious health problems. These hairy nanoparticles are able to readily clean water. For example, here we have a copper solution that we add electrosterically stabilized or anionic hairy nanoparticles to it, and within minutes we can see a precipitation of copper nanocellulose aggregates, and the supernatant will be a clean water. And the removal capacity of these nanoparticles is almost 40 times the removal capacity of activated carbon. The structures that we get by adding hairy nanoparticles to ionic solutions can be raft-like aggregates when we fully neutralize the charge on the particles, or stable star-like aggregates when the charge on the particles are partially saturated so that they come together from only one end. We can also convert these additives into hydrogels or aerogels through simple chemistries. For example, here we are reacting bifunctional hairy nanoparticles functionalized with aldehyde and carboxylic acid with carboxylated chitosan to form these hydrogels through shift-phase reaction, followed by removing water phase to get this extremely light material we call aerogels that you can see we put it on a plant and it doesn't even move it. The structure is highly porous and it can be used for water treatment, for example, removing dyes from water or even heavy metal ions and precious metals and so forth. So this way we actually fix these nanoparticles. We don't need to add it, so we can have cycles of removal and recovery. We can also use these particles and incorporate them into paper and cross-link them with green binders such as ammonium zirconium carbonate to improve the mechanical properties of papers and replace the environmentally unfriendly latex particles. We can improve the storage modulus, for example, here, as you can see, by more than 5 times, for example, using these hairy nanoparticles and get a better quality coating with less number of cracks compared to conventional nano particles. Another application is antibacterial applications that was done in Theo's lab. We can use these hairy nanoparticles, particularly here we are dealing with a neutral nanoparticle with aldehyde functional groups to fix natural antibiotics such as niacin on that to increase the stability of these antibiotics and kill more number of bacteria per unit mass of these bactericides. Over 24 hours, the stability of these natural antibiotics go down and decrease, and while we basically functionalize hairy nanoparticles with antibiotics, we see an improved antibacterial performance of this bacteria. And this work is the work that was recently done in Theo's lab, which is pretty interesting. Another interesting application is to use nanocelluloses for humidity switches. We can mix conventional nanocelluloses with carbon nanotubes, which are basically conductive, or we can mix these hairy nanoparticles with CNT, carbon nanotubes. The conductivity of nanocomposites made of conventional nanocelluloses and CNT, as you can see here, is almost constant versus relative humidity. But when we are dealing with these hairy nanoparticles, the conductivity is noticeably low at low relative humidities. And suddenly, after 60% relative humidity, the conductivity starts increasing. So initially, at low relative humidity, these hairs act as barriers, and as the humidity increases, they start connecting this material as they basically get hydrated, and the conductivity increases. So we can think about these materials as humidity switches that can respond to different levels of humidity. This is probably an interesting applications that we noticed about hairy nanoparticles. Typically, conventional nanocelluloses are used for increasing the viscoelastic properties or increasing the storage and loss moduli of materials such as hydrogels in the form of nanocomposites. And as I see here, cellulose nanocrystals and cellulose nanofibrils increase the storage modulus of a model gel by increasing the concentration of these nanoparticles in the network of the gel. But what we observe with hairy nanoparticle is that not only doesn't decrease it doesn't increase the storage modulus. By increasing the concentration of these hairy nanoparticles, the storage modulus decreases, meaning that they prevent or impair the formation of network, because the early stage monomers absorb on these hairs, and then the electrostatic and steric repulsion between these hairy nanoparticles keep these monomers separate from each other, preventing the formation of a strong network. And this can be used for developing highly soft hydrogels for a variety of applications, such as oral drug delivery systems. Having this said, I would like to conclude today's talk by telling you that hairy nanoparticles can be prepared through facile chemical methods, as I mentioned today, and they overcome some of the key limitations of conventional nanocelluloses, as I showed here, and open up opportunities for applications that conventional nanocelluloses would not be able basically to do. These hairy nanoparticles can provide reliable and green scale inhibitors and inhibition solutions, and we can make scale-resistant membranes. They are good candidates for water treatment and many other applications that I mentioned in today's talk. Finally, I would like to thank many people that I worked with in the past couple of years, particularly Theo Vandeven and all the students in his lab, and financial support in the past couple of years from both Canada and US supporting my work. And I would like to finish my slides by telling you that please feel free to reach out to me if you have any
Mayor, that was
questions, if you
perfect.
need this
We're right
material to
on
test
time,
in
but
your
folks, we're
labs,
going to spend
if
a
you would
few
like
extra
to
minutes
collaborate, or if you are
doing a couple
trying to
of
make this
questions
material
with
and you
Professor
have
Shaky, and you're welcome to stay, but
questions
if you have
regarding
to
that.
go in the
Thank you very
interest of
much, and I'm
time,
more than
we
happy
certainly
to
understand that.
take any questions.
Trevor, let me turn the question floor to you. Go ahead.
Thank you, Mike. So, Dr. Shaky, record number of attendees on for the webinar today live, so that's wonderful. And several of them had questions related to surfaces and surface passivation and adhesion of the hairy nanocellulose. So maybe you could comment about the use of these materials as surface modifiers rather than bulk water processing.
Definitely, definitely. Well, again, thank you everyone for being here. I see more than 100 people here. This is amazing, and I had a lot of fun today. This is a great question. So, hairy nanoparticles can be produced in different forms. We can have anionic versions of that with carboxylic acid groups or other types of anionic groups, neutral versions of that with aldehyde groups, and positively charged version of that with, for example, amine groups. So depending on the chemistry of the surface, we can think about chemical conjugation of these nanoparticles with the functional groups of on the surface. For example, if we have a surface that has, let's say, amine groups, and we want to readily functionalize it with hairy nanoparticles, simply using aldehyde functionalized nanoparticles will result in a sheaf-based reaction between these hairy nanoparticles and the surface, and conjugating them to the surface. And I see one question, how niacin is conjugated to nanoparticles. It's very similar,
I have another question if I
depending
could
on the
Well, a
jump in.
functional
fascinating
groups
talk, Dr.
of
Shaky.
the
Thank you so much. Why don't
surface
we hand
or
back
a
to...
target molecule. We can
Thank you,
tune
Trevor.
the chemistry between
We're just
the
going to do one more. There's a
nanocelluloses
bunch in the
and that
chat window, but I
target.
appreciate everyone's interest. But I think there's a chemical engineer amongst us out there, because the question is, what if you're using these things in high temperature or high pressure heat exchangers as anti-scalants? Will they last? What are the temperature dependent properties of these sort of things? Uh-huh.
Yeah, that's a good question. The highest temperature that I actually tested their anti-scaling properties was about 50 degrees centigrade.
Sure.
Now there is room to study their performance at higher temperatures, but cellulose itself should be stable
That
up
makes
to
sense.
80, 90
Thanks for that
degrees
response.
centigrade. Of course, over
Amir, thank you
time, we
again for
may
the
see some
presentation. And colleagues,
degradation.
although we didn't
But
have time
going
to address all
above
of your
100
questions
degrees
today,
centigrade will
we did take some of
probably
them. Trevor, thank you for
jeopardize
your
the
participation, and
structural
Bob Ehrman
integrity
from
of
Penn
cellulose.
State. I'd like to invite all of you to join us for our next webinar. We're on a big nanomaterials tear here. It's on May 14th, luminescent nanoparticles of metal oxide. So instead of these softer celluloses, we're going to be going to the hard side of nanomaterials. So please join us then. Today, I'm going to ask one last thing of our audience. I'm asking you all in the chat window to acknowledge the presentation by Amir. If you just give him your thanks in the chat window, he'd appreciate that. And while we're doing that, I'm going to launch a very brief survey. It's going to open in a new browser window. There's just 4 questions. So take a moment to respond to that survey, and that helps us improve our presentations. So here we go with the survey launch. You'll still hear my voice as the survey comes up into another browser window. And so there it is. Thank you everyone for joining us today. That officially ends the audio portion of our webinar. I'll leave the system open for a few minutes so you can use the chat window and other things. Again, thank you for joining. Goodbye to everyone.